Okay, so surface integrals. So in the previous section, we integrated areas, but what's happening here is we're just basically adding functions here. And there's the two different kinds. This is when you have z equals g of x and y, then you just use this. Okay, but if you just have parametric equations in two variables, and you have the r of uv equals something, then you just use that. Okay, and then also this right here. So z sub x would be the partial of this with respect to x. Z sub y is the partial of this with respect to y. So let's do a few exercises. We'll start with number 1. So the integral over the surface. So in the previous section, we did a few integrals where we're just finding the area. So that would be the same as if there was this y wasn't there. Okay, but here we have the y there. Okay, so what's the first thing we should do with this to calculate the integral here?
Do you take the cross product of the
Yes. Good job. You realize that you have this situation here because you have this r of uv. You don't have z equals something. So you have this situation here. So we're going to take ru cross rv. Okay, and I'm just going to go ahead and do it right here. Okay, so what's r sub u? So here's.
You mean the differential of that?
Yeah, so the partial of all of this is u.
Wouldn't that be just cosine v?
Yeah, and then
sine v, and then v.
0.
Oh, 0.
Because this is.
Oh yeah, because that didn't have
u. Now with respect to v, it's a little bit more complicated. So negative u sine v, and then this one would be u cosine v, and then this would be 1. Okay, I'm going to put it in this notation here. So let's see, you have I times this, so that's sine v. But then you have this going back this way, you got the 0, so that's 0. So that's your I component. Now your j component will be this times that's 0 minus this, so that's minus cosine v. Then your k component is going to be this times this minus that times that. So that's u cosine squared v. Okay, minus, but there's a negative here, so that's plus u sine squared v. Whoa, this all just becomes u. So this u. And it's the magnitude that you're after. So it's the square root of sine squared v plus cosine squared v plus u squared, which is just going to be 1 plus u squared to the 1/2. Wow. All right. Okay, so now the integral. We're going to multiply by that, but the y, let's see, what's the y here? That's this one here, right? So we have u sine v. Okay, and then this one, we have this 1 plus u squared to the 1/2. And then let's go du dv. What's the limits of integration?
Is it 0 to 1 or 0 to?
Zero to 5.
Yeah, you look over here. So 0 to 5, and then v goes from 0 to pi. Okay, so let's integrate that part. So that's going to be, I mean, this comes up a lot here when you're doing these exercises. These kind of integrals come up a lot. I think it's just because they're looking for stuff that you can actually do. It's not like impossible to integrate. Okay, there's no v's in here, so we can go ahead and just integrate that. So that's going to be negative cosine v. And that's going to go from 0 to pi. And this part right here, if you put a 5 in, what's that, 25? Whoa. So that's 26 root 26. Minus, they put a 0 and that's just 1, so minus 1. Wow. This one, meanwhile, is going to be negative cosine pi. This one is going to be negative cosine pi is negative 1, so that's 1 minus a negative 1. Okay, because you put a 0 in here, you're going to get negative 1, but you're subtracting it, so that's going to be 2. Okay, so 2/3 times 26 root 26 minus 1. Okay, so go ahead and try that one. Okay, so that's another one. Evaluate the surface integral. So x squared yz. S is the part of the plane that lies above the rectangle, 0, 3, 0, 0, 0, 2. Okay, so here you have z equals, right? Z equals. So that means that we can use this part right here. We can use this part here. And zx would be what?
2.
Exactly. And zy would be 3. Okay. So the partial of this is respect to is to 2, and then this is just a 3. Okay. So that means that the integral let's go ahead and set this rectangle up. But let's put this part in first. So you have x squared y z, right? So what you need to do is take this z here and replace it with this. Okay, so you cut back down to 2 variables. You can't have you can't have a double integral and doing 3 variables. That's not going to work out too well. And then this is the 1 plus this squared plus zy squared, so 9. Okay, and then if we go, let's go dx, dy. So what's the range on x?
0 to 3.
Yes, yeah, good. And then the range on y is 0 to 2. That's what you look at right there. Okay, so this is the square root of 14. So let's pull that all the way out and put it in the timeout box right there. And distribute that in so you have x squared y plus 2x cubed y plus 3x squared y squared dx dy. Okay, now we integrate in x first. So what are we going to have? I'm going to integrate in x.
X over 3 to the power 3. 3.
Yes. Times y. And then this one?
Half x to the power 4. Y.
That's going to be over 2 because you have a 2 there already.
Mm. And so it's just going to be x to the power cube y squared.
Right. Okay, and so that's going to be evaluated from x equals 0 up to x equals 3. Okay, so if you put a 3 in here, you're going to get 27 divided by 3, that's going to be 9. 9y. This is going to give you, whoa, that's 81. 81y over 2. Dang. And this is going to give you 27y squared. And so I'm just going to go ahead and integrate that one. And that's 9y squared over 2 plus 81y squared over 4 plus 9y cubed. And that goes from 0 to 2. Okay, so you put a 2 in. And if you put a 2 in there, that's going to be 18. Put a 2 in there, then the 4s will cancel, so that's just still 81. And then the 2 in here gives you 72. So 107, and these add up to 171. 171 for root 14. Okay, great. Let's go to the next exercise. If you have any questions, just speak up, please. Or if there's something that you don't understand very well. Okay, so here we have evaluating the paraboloid. And here we have x equals y squared plus c squared, given by x is between 0 and 1. Okay, so let me show you a little trick, which you might have already figured out. And that is that these variables x, y, and z, you can like shift them around, that's okay, and let them play different roles. So basically what I'm going to do is I'm just going to swap x and z. Because here I have x equals something, so you have a paraboloid, x equals something, right? If this was z equals something, then I could just use the formulas on the first page, right? So if I swap x and z, then if I swap them here, then I get z equals y squared plus x squared, and here I get this, and then over here I get x squared ds. Okay, and this and all this, if I do this problem here, it's going to give me the same answer as that one would. Exactly the same. So I do this problem instead, and that way it's easier for me to apply the formulas and stuff. Okay, does that make sense to you guys? So everywhere I see an x, I put a a z. And everywhere I say a z, I put an x. Okay, so that x got replaced with that z. That z got replaced with x. That x got replaced with a z.
Are we gonna switch it like at the very end?
No, because what happens is the end is going to be a number. So it doesn't matter. So the end, so like the previous, so when you do these surface integrals, you're going to get numbers as answers, so it doesn't matter. Okay. So whether, I mean, another thing you could do is just keep the x's, just keep the stuff, and then try to, and then as you go along, try to modify the formula. So here it would be, instead of f of xy, g of xy, it would be f of g of yz, comma y, comma z. And then this would be 1 plus x sub y squared plus x sub z squared. Okay, you can try to do that one, follow along that way. But it's, because it's much easier to do this way though. Okay, so let's go ahead and calculate the integral. Okay, so we're going to go over d instead. And this x squared, that's, now you just need to get everything in terms of x and y. And this is x, so you're fine. And then you have the square root of 1, and then z sub x squared. What's z sub x?
Two x.
Yes. So this will be 4x squared, right? And then z sub y is 2y, so this will be 4y squared dA. Okay, now we have to figure out what region are we going to integrate this over? Now, if z is ranging between 0 and 1, and z is also equal to x squared plus y squared, then when you see x squared plus y squared, what do you have the urge to do?
Make it r squared?
Yeah, make it r squared. So make it polar coordinates, okay? So r squared is z, right? So basically you have that. Now, if z is ranging between 0 and 1, then that means that r squared is ranging between 0 and 1. Okay, so r is between 0 and 1 as well. Okay, so what makes sense is for us to change to polar coordinates like that. And then right here, you notice that this is 4r squared, right? So we have, what do we have? We have 1 plus 4 r squared to the 1/2. This is nasty. So x is r cosine theta. So you got r squared cosine squared theta. And then the limits on theta, 0 to 2 pi. Because it didn't say anything about restricting to the first octant or anything like that. So 0 to 2 pi would be good to go. Okay. So you have cosine squared theta, and you have r cubed times 1 plus 4 r squared to the 1/2 dr d theta. Unfortunately, this is kind of nasty. But we have Symbol Lab to help out with, and I figured this out with Symbol Lab. You can use integration by parts. Okay, would do the trick. Let U be this one, and wait.
I'm sorry, I had a quick question.
Okay, go ahead.
Why is the first one R to 0 instead of 1 to 0?
Oh, that's true. Yeah. Because that's not an R, it's actually a 1. It just looked like an R.
Oh, sorry.
Okay, no, thank you. Thanks for pointing that out, because I noticed probably other people didn't see that it looked like a 1 either. Okay, so moving along. So you integrate that part with Symbol Lab, and I got 1 over 120 times 6r squared minus 1 times 4r squared plus 1 to the 3 halves. Okay, and that's being evaluated from 0 to 1. Okay, now there's no thetas in there, so that means that we can go ahead and evaluate this one while we're at it. So if I evaluate that, that's going to be 1/2 theta plus 1/4 sine of 2 theta. Okay, and so that's just this part here, the d theta, and that's going to go from 0 to 2 pi. Okay, over here, if you put a 1 in, let's see, what do you get? You put a 1 in here, you get 6. 6 minus 1 is 5. And then this is, you put a 1 in here, you get 5 to the 3 halves. That's 5 root 5. And then if you subtract and put a 0, if you put a 0 here, you get -1. So subtracting is actually going to be plus. And that gives you 1. So it's just going to be 1. Cool, that's it. Okay, so over here, if you put a 2 pi in here, that's going to give you 2 pi over 2. That's all 0 because, you know, putting a 2 pi in there, that's 0. And then the lower limit's also going to be 0. So that's just going to be pi. And this part is 1 over 120. Those are going to cancel. Times 25 root 5 plus 1. Okay, so that's going to be pi over 120 times 25 root 5 plus 1.
Question.
Yes.
Is it supposed to be 25 root 5 plus 5? Since it's in the parentheses? No.
Okay, so if you put a 0,
Oh.
1.
Okay. Yeah. I got it now. Thank you.
Okay. Sure. Okay, so great. That's number 3. So let's move along to number 4. Evaluate this one. So you have S as the hemisphere. X squared plus y squared plus z squared equals 4. Okay, what you want to do is actually go to spherical coordinates. Dang, I was going to put them here, but I forgot. Okay, so, but I'll just write it out. So spherical coordinates, X is rho sine phi cosine theta. Okay, Y is rho sine phi sine theta, and Z is rho cosine phi. Okay, so that means that this hemisphere can be described in terms of phi and theta, because this is, what's the radius of this hemisphere?
Two.
Yeah, that's 2. So just replace all of these with 2's. So 2 sine phi cosine theta, 2 sine phi sine theta, and then 2 cosine phi. Okay, that's all that. And you also, okay, so when you do this, you also need limits on phi and theta. Okay, so let's go with theta first. What do you think the limits on theta? That's the easier one.
Would it be? It wouldn't be 2 pi, right? Or is it? Oh.
It would be, because you're going all the way around. This hemisphere is going all the way around. Okay, phi is a little bit more tricky, but I think you guys can figure that out. What are the ranges? So remember, phi is the angle with the positive z-axis. So phi equals 0 is actually pointing straight up. So it's going to go from 0, and then you want it to go down to the xy plane. For any value in the xy plane, what is phi? If you have something in the xy plane, what is phi going to be?
It'd be pi.
No, it's going to be, no, not pi. It's going to be pi over 2. Because yeah, if you're here on the x-axis and then here on the y-axis, this angle is pi over 2. It's 90 degrees, right? So from the positive z-axis to anywhere in the xy plane, it's a right angle, the angle between those 2 points. Okay, so this is all the information that you need to set everything up. And so you want r phi. Wait. Cross r theta. Okay, hold on, I need more space. Okay, so what's r phi? That's the partial with respect to phi. It'd be 2 cosine phi cosine theta. And then the j component will be 2 cosine phi sine theta. And the k component would be negative 2 cosine, no, sine phi Dang, this is like crazy. Okay, and with respect to theta, we get -2 sine phi sine theta. And then this one gives you 2 sine phi cosine theta. And that one, fortunately, gives you 0. Okay, so I calculated this. Do you guys want to see the calculation, or do you want me to just tell you what it is?
Depends what's going to be on the test.
Okay.
Just tell us.
Okay. It's gonna be 4 sine phi. That's what it's gonna be. One thing. That's what it turned out to be. Everything, it just canceled all the way down to that. It just went all the way down to that. So let me do something really quick here. Do you guys remember what remember what section with spherical coordinates was? Oh, it's 15.8. Okay. Okay, so can you see this? Let's see. Of course, you can see that. Okay, so you see how when we were doing spherical coordinates, how we have this right here. dv is rho squared sine phi, blah, blah, blah. And you see that rho squared sine phi right there? Well, so rho squared sine phi, that's basically what that is. Okay, rho squared sine phi is basically what that is. So part of the dv thing. Okay, so anyways, let's continue on. So the calculation is pretty much the same as for that one. Okay, so the integral now, so you want to set that up. The integral is, okay, so let me get this part. So there's this part right here. And that is, you can split it up into x squared plus y squared times z. ds. Okay, now let's go ahead and change everything into spherical coordinates. So what is x squared plus y squared?
Or r squared.
R squared.
R squared.
No, that would be, okay, that would be That would be polar coordinates. But we need to get everything in terms of phi and cosine. We need to get everything in terms of phi and theta. Okay, and so this is x, and that's y. So that's x, that's y. So x will be what? So x squared, okay, this is x, and x squared is going to be 4 sine squared cosine squared, right? Okay, so 4. Let's do an intermediate step. So that's 4 sine squared cosine squared, and then y is 4 sine squared. Okay, that's theta. They're different. They're different. See, and then sine squared theta. Okay, so notice that these two are the same, right? You got cosine squared of theta plus, and then sine squared theta, and everything else is the same. So this is just going to end up being 4 sine squared of phi. Okay, so that's your x squared plus y squared is that. Okay, now the z, what's z? It's just this, right? 2 cosine phi. That's our z. Okay, and then for the ds, we've replaced that with what? With this.
Netty.
Okay, and then we'll go d phi, d theta. So what? The limits on phi are 0 to pi over 2. And the limits on theta are 0 to pi. I mean 0 to 2 pi. Okay, now there's no thetas in here at all. It's all phis. There are no thetas in here. So that means that this is just going to be 2 pi. And then you have a 4, wait, we'll leave that there. Okay, then you have 0 to pi over 2. And you have 4, 2, and 4, so that's 32. And then you have sine cubed of phi cosine phi d phi. Okay, great. So now, question: what's the integral of this? Or what's an antiderivative? This one should be easy.
Oh, it's a special one. Dang it. Oh.
It's sine 4 over 4.
Yes, sine 4th over 4. But since we have this 32 over here, we can just divide this by 4, right?
8.
Okay, and then plug up pi over 2, that's 1. 1 to the 4th is still 1, so that's going to be 8 times 2 pi, so that's 16 pi. Subtract, plug a 0, and that's 0. So evaluate the surface integral for the given field F and the oriented surface. In order to find the flux of F across S. So you have this vector field, and vector fields are kind of action where you've got little vectors pointing in different directions, and you can kind of think of it as a fluid flow, or maybe a magnetic field or something. But you can think of it as motion in different directions, okay? And the flux across would be like how much, so like for example, if it was motion of water and you had like some surface, not really a surface of an object, but just like some area or some place, and then the flux would be the amount of water that's going across there. that's flowing past. Okay, in a certain direction. So it's also directional. Okay, and so they, for example, they say for closed surfaces use the positive outward orientation. Okay, so this one I don't think is a closed surface, so it doesn't really apply there. But anyways, when you have surfaces, you're going to use the outward orientation. Okay, so the first problem, here's the vector field, and then S is the part of the paraboloid that lies above the square. Okay, so this one's probably the most straightforward of all. Here's the formula right here. If you just have the surface and parametric equations, then you're going to use this one. But here, this one right here, this is for when you have the surface z equals something. Okay, so that's this one. And so we're in this case right here. This is the one that we're going to be using. Our P is going to be xy. Our Q is going to be yz, and our R is zx. Okay, now we're supposed to calculate zx. That would be the partial of z with respect to x. So we take the partial with respect to x, that's negative 2x. The partial of z with respect to y is negative 2y. And I think we have everything we need to do. This is going to be where you integrate. So I think we can set everything up. So we'll use this last one here. Let me write this down. Let me do it on here. Okay, so you got x and y going from 0 to 1. And then negative p, so that's negative xy. So that's that one. And then your zx is negative 2x. And then you have minus, and then you have q, which is yz right there. And then your zy is negative 2y plus zx right there, your r. And that's dA will be, we'll just go x dx dy. So that's just hopefully pretty straightforward. It's just a big integral, that's all. So this is what, 2x squared y plus oh, I made a huge mistake. I made a mistake. I wasn't thinking. This z right here, I should have replaced it with this. Okay, so that's bad. Okay, hold on. Let me erase all that. So I'm sure you guys will never make that mistake. So yz would be y times this, 4 minus x squared minus y squared. And then your zy would be negative 2y. Okay, and then the r is going to be, okay, that's zx, so z is this, so 4 minus x squared minus y squared times x. Okay. So we have 8, okay, so this times that is 8y squared. And then we have this times the middle one, so that's minus 2x squared y squared minus 2y to the 4th. That would be this, and this. Okay, and then over here we have plus 4x minus x cubed minus y squared x. So much. Looks like it just became a lot harder. Okay, so then you just integrate that. It's also from 0 to 1. So integrate in x. So just integrated x first. So you got 2x cubed y over 3 plus 8y squared x minus x cubed, no, 2x cubed y squared over 3 minus 2x y to the fourth plus 2x squared minus x to the fourth over 4 minus y squared x squared over 2. This is crazy. So much stuff here going on. Okay, so you're going from 0 to 1, and then you're going to integrate in y. Wow. Okay, so this is 2/3 y. So basically just put a 1 in for everywhere you see an x. So that's not too bad. 2y squared over 3 minus 2y to the fourth plus 2 minus 1/4 minus y squared over 2. See, the problem, what makes this so hard is that you could easily make one mistake here somewhere, and then it's like take you forever to figure out what happened. I guess I didn't need to do it that way. Okay, so now we're integrating in respect to y, and that's going to be y squared over 3 plus 8y cubed over 3 minus 2y cubed over 9 minus 2y to the fifth over 5 plus 2y minus a fourth y minus y cubed over 6. Right here from 0 to 1. Okay, so this becomes 1/3 plus 8/3 minus 2/9 minus 2/5 plus 2 minus a fourth minus 1/6. And I just threw it in the calculator and came up with 713 over 180.
Wow.
Yeah, so that works for you guys?
Yeah, it worked.
Great.
It worked.
Wow, yes. So that's a lot of computations that you have to not make mistakes on. So that's the thing about that. Okay, number 6. Okay. So this is a similar problem. I'm going to do the same thing here. Evaluate the surface integral, and this time f is yj minus zk, and that's consists of the paraboloid y equals x squared plus z squared, y is between 0 and 1, and the disk. Okay, so what's happening here is that you have this parabol. Okay, so you have this paraboloid here. So this is kind of awkward because this is y equals, right? This is y equals on the paraboloid. And so we're used to having z equals. So you can do that one trick that I told you about. Right? And that is to swap z and y. So everywhere you see a y, put a z. Everywhere you see a z, put a y. And then also, if you're going to do that, then you have to swap the j and the k. Okay, just to be consistent. Okay, so this becomes and that changes to a z, right? And this changes to a k. And then the z changes to a y, and that changes to a j. Okay, so that's when we're swapping this. and then this becomes, the parabola becomes z equals x squared plus y squared. So the z changes to that and the y changes to that. And then this one right here, that changes to this. Okay, and then this disk right here changes to x squared plus excuse me. Let me change this to a different color. Okay, so this changes to x squared plus y squared less than or equal to 1. And then, so this z changed to y, and then this y changes to a z also, z equals 1. Okay, let me give you a little, just a kind of a brief idea of what this looks like. Okay, so now at this point, so we're looking at the new one that I did, not the old one. So if we just turn everything around and then treat the vector field as is different, then it's going to work out okay. So you have this paraboloid here, right? And this paraboloid is going to be on the bottom here, coming up. Okay, so in all these directions here. Just kind of a bowl, a parabolic bowl. And then on the top, it's got this disk on the top, right here. So this is an enclosed area. This is enclosed. Okay, so you're looking at, so you imagine what's the overall fluid. So like if you've got a bunch of fluid flowing around here, what's the overall fluid flow on this thing? What's the net? So you're thinking about, okay, what's the net fluid flow? Is there more fluid going in, or is there more going out? Okay, what's the net effect? That's sort of what we're looking for right there. Okay, now to find that, we have to find the flux over the parabolic surface, and we have to find the flux over the top, okay, of it, which is the orange part. So we have to do those separately. Okay, so for the first one, we have this z equals, right? So we can use the formula that we can use the formula from the previous section, which is this one. We can use this formula here. Okay. So go ahead and we'll go ahead and set that up. So from here, we can identify what the P and so P is going to be 0 because there's no I component. And then what's Q going to be? That's going to be this one here, which is negative y.
Mm-hmm.
Negative y. And then R is this z. But what's going to happen is we're going to eliminate all the z's when we do the integral. And so you change that to, so really what you're going to have is x squared plus y squared, this one here. So z is x squared plus y squared. So we're going to have that. So that's our P, Q, and R. Okay. So that's what we're going to go with there. Now, let's see, what do we do now? Yes. Okay, so now we have the integral. I have to look at the formula because I don't have these things completely memorized. Okay, so this is negative P Zx minus Q Zy plus R dA. Okay, so negative P, that would be 0. So that's going to be 0. So that one's 0. Maybe I should down on here. Let me do it down there so you guys can see better. Okay, that's 0. So who cares what that is? And then Q is negative Y. That's negative Y. And now Zy. Okay, here we have Z. So Z sub X is 2X and Z sub Y is 2Y. Except the problem is, let's see here. So we're on the bottom part of the bowl, right? So we're not. So let me think. Yeah, so that's just going to be, that's going to be 2Y. It's still going to point outwards. And then R is X squared plus Z squared. Okay, now, but this one, oh dang, now I'm really confused. We might have to make that point downwards. We might have to make that negative. But here's why, dang, here's why I don't here's what I don't know. Oh. What do you guys think? Should we make that point downwards? Because we're on the bottom of the bowl, right? We're looking at what is it going out of the bowl, and then downward, the outward direction. So the outward, use the positive outward. So outward is positive. That means that, okay, oh, down is positive? We'll just use X squared plus Y squared, okay? Okay, and then that's dA. Okay, it's best if we flip this to polar coordinates, and in that case, we're just gonna have R go from 0 to 1, and theta go from 0 to 2 pi. Because, okay, look at the picture over here. We're really integrating across, if you project this down, we're really integrating across this circle down here in the XY plane. That's really what this D is. Okay, D is the circle down here that we're integrating across. Okay, and so then D is given by this, and that's where the action happens. Okay, so we have this is 2y squared, and then this is going to be r squared. Okay, so but y is 2 sine, no, y is r sine theta. Okay, so that's r squared sine squared theta plus r squared, and then your dA becomes r dr d theta, like that. Okay, so now we have 2r cubed sine squared theta plus r cubed dr d theta. You integrate with respect to r, and we have r to the 4th over 4. So these are going to be r to the 4th over 4. Basically, the overall effect after you do that is going to be to put a 1/4 out there. Okay, now integrate with respect to theta. The integral of sine squared is
Cosine. Oh no.
yeah, it's 1/2 theta minus 1/4 sine of 2 theta. That's a weird thing. Plus theta there. Ah, this goes from 0 to 2 pi. Okay, so this part's just going to be 0 because you put 2 pi in, you get 0. You put 0 and you get also 0. So that's all 0. So that's good. Okay, this one, and so then we have, this is going to be 2 pi. And then these cancel. So it's going to be 2 pi. Plus another 2 pi from there. So that's going to be pi. Okay, now we also have to do this top part right there. And for the top part, okay, so for the top part, again, we have f is, I'm going to just copy this down. So negative, let me do it over here though. So we have f equals negative yj plus zk. Okay, so again, p is 0, q is negative y, and r is z. But z is 1, so this time r is 1. And the surface is actually z equals 1 is the surface. This is the surface. And this is just where it is, okay? So the surface is equals, the surface of the top is just z equals 1. So that means that zx is 0 and zy is also 0. So when you go to take the integral, I think I made a mistake here. All this should be negative. And that should be negative pi. Because we're underneath, okay? So everything negative. So I'm just going to do that. Okay. And so then this becomes that's 0, and that's 0, just because those are 0. And then r is 1. Okay, so if you integrate that, you just get r squared over 2. And then because there's no thetas in there, then that just becomes 2 pi. And you integrate that, and you get r squared over 2, and that's the value from 0 to 1. So that's going to be 2 pi times 1/2, which is pi. Okay, and then what happens is the final thing that you do is you add these together, and that gives you 0.
I hate answers that come to 0. It's like we did all the work for nothing.
Yeah, indeed. That's for sure. Yeah. Now there's a theorem in the following sections that will basically, I think it's, you can look at this and determine, it's going to be 0. You can just look at the field.
Really?
Okay. Oh, that's going to be 0. I think so. We'll see. We'll see. I'll say maybe. Okay. Okay, so let's look at number, so this is really weird. This looks like a bowl of soup right here. Oh, interesting. Okay, so let's take a look at and getting all the signs corrected, that's a little bit tedious too. So that's another thing that's just weird. Okay, so number 7. Okay, so here we have, evaluate the surface integral for a given vector field F and oriented surface S. Find the flux across S. Okay, so here's the vector field. And then S is the boundary of the solid half cylinder. So Z goes from 0 to the square root of 9 minus y squared. And X goes from 0 to 2. So let me try to draw a picture of that for you guys. Because that helps quite a bit if you can do that. So here's the z-axis, the y-axis, and then the x-axis there. Okay, so now x goes from 0 to 2, so I'm just going to mark out, make this go just a little longer, and to say that's 2 right there. I'll say that's 2. Okay. Okay. So let's see here. We have, if you look at just y and z, and you square both of these, you get, like if you set it equal to each other and square it, you get this. So you bring the y over, you get y squared plus z squared equals 9. So that means that's a circle of radius 3, right? But you just want the top part where z is greater than, so z, you just want the part from z, above the xy plane. Okay, so that's a circle, and it goes about the x-axis. So if you come out, and the radius is 3, right? So if you come out here to 3, and then n over here to 3, and then up here to 3, then you have this kind of half circle right there, right? And then, but it's a cylinder, so it comes out this way. So it comes out that way and then goes over like that, right? Okay, so something like that. Okay, now it's got this top part right here. And then it has the base here. This base right there. And then not only that, but it's got a backside. And it has a front side. Okay. So let's do this. So first of all, so you got to do you have to check 4 integrals. Boo, 4 integrals, boo. Okay, so the first one, let's see here. Wow. Let me show you. So this is the top part. Let's do the top part first. Now let me show you, because we haven't used it, and this is the very last problem. Let me show you how you would use the second formula. So that one would be, so the second formula, or I should say the second to the last formula is this one right here, where you've got the cross product in there. Okay, F dot R U cross R V D A. Okay, so let me show you how that would work. So even though I guess maybe it's not really set up for that, but anyways, so if you think of just the blue top right there, you can actually do it in X and Y, and that's going to give you X, Y, and then the Z part would be this one right here. So the square root of 9 minus y squared, or 9 minus y squared to the 1/2. And then this, so the U and the V are X and Y. So you got RX cross RY. Okay, so RX, you're taking the partial of this with respect to X. That's when I like that one a lot, because that's just 1 and then 0, 0. Those are both 0. Yay. And then RY would be 0 and then 1. And then this one, this is the worst. This is the worst. That's negative y times 9 minus y squared to the negative 1/2. Okay, so copy down the first 2 columns and take the cross product, and that's going to give you 0, 0, k. And then minus, and then 0, 0, and then bang. Minus this, which is plus y times 9 minus y squared to the negative 1/2 j. Okay. Or if we take this to the back, we got right like that. Now this one says take the vector field and take the dot product of this with this. Okay, so F is this one, x squared, y squared, and then, but this last one you have to replace this z squared with this. Okay, so taking the dot product of those, is going to be x squared times 0 plus y squared times y times this. This is over, again, I'm going to write it over that, 9 minus y squared, plus this one times k. So that's times 1, I'm sorry. This times 1, so that's 9 minus y squared to the 1/2. Okay, great. So now the integral becomes, this integral becomes this. Now, you're integrating over this bottom rectangle. You integrate it, because that's, this bottom rectangle covers all of, is like the projection of every point on top down to the xy plane. Okay, so x is going from negative, so y is going from, no, x is going from 0 to 2. We'll go x first, okay? And then y goes from negative 3 to 3. And you're integrating this. So this is y cubed over the square root of 9 minus y squared plus oh, I made a mistake. This 1/2 shouldn't be there because it's squared. Z is squared. So it's not this, it's this squared, which is 9 minus y squared plus 9 minus y squared. Okay. So we just have to integrate that. Now, out of these three terms, if I said you could snap your fingers and get rid of one of them, which would you get rid of? The first one, right?
Yeah.
Come on, you guys. Yeah, this is the worst one. That's going to be 0. Okay. The thing is, yeah, why is that going to be 0 when you integrate? Anybody tell me?
Because it is.
It's an odd function. Okay. So what that means is that, so if you have an odd function, what that means is you're symmetric through the origin. Okay, so this is an example, right? This is an example, maybe something like that. That's probably not a very good drawing. Here, let me try to fix this. Okay, so let's say we have that, something like that. Okay, and you integrate from here to here. Well, it's going to be this area minus that area. And if this is symmetric through the origin, then these areas are going to be the same, right? Going from negative 3 to 3. You're going from some value over here to some value over there. So the integral is 0. From negative a to a, if you have an odd function. If you have an even function, that doubles up. Okay, so 0 to 2. Now this one, when you integrate, you get 9y minus y cubed over 3, evaluated from negative 3 to 3. There's no x's in there, so I guess that we could just say that's going to be 2. And here, what's this? You put a 3 in there, you get 27 minus 2703, so that's minus 9. And then you subtract and put a 3 in there, so that's going to be plus another 27, minus another 9. Which turned out to be 72. Okay, so that's just the top part, but that's the hardest one. That's the hardest part. Okay, now let's go for the base. So this green part down here. Okay, so that's this down here, the base. Okay, the green part. Okay, now, what's an equation for the base?
The base isn't just a square.
Uh-huh. The surface. It's a part of a plane, right? Well, it's part of the xy plane. And what's the equation for the xy plane? Z equals 0, right?
Oh, yeah.
Now, another form of this is this one, f dot n ds. Okay? And if we say, okay, f dot n, okay, what's the normal to this one? The normal that points outward. So if you have, so in other words, you take a point here and it's going to be pointing straight down, right? That's like negative k, right? The normal is negative k, right? And so f dot n is going to be this dot. Okay, so that's 0, 0, negative k, right? Okay, so f dotted with this is just going to be z squared, which is going to be this times 0 plus y squared times 0 plus z squared times negative. Okay, so it's negative z squared. But z is 0, so that's just going to be 0. Okay? So for the base, this part is going to be a big fat 0. Okay, so we got two things down. Now, let's do the back side. Okay, so back here. And what's the equation for that? For the back side.
Y-axis would be like y equals.
Not y equals.
Oh, never mind then.
It's, by the way, it's this part of the equation right here. So it's x equals 0
Okay.
is the back side. And what would the normal be? So that would be the pointing out. So if you got a point here on the surface, it's going to be pointing that way, right? So what would that normal be?
Okay, so if it's that negative k, oh,
Which direction is it pointing? What is it? Is it pointing in the x direction, y direction, or z direction? By the way, here's x, right? This is the x direction. Here's the y direction along the y-axis. Here's the z direction.
Pointing the x direction?
Yes, it's pointing it's pointing backwards in the x direction, right? So that's it right there. Okay, now f dot n is going to be this one, negative x squared. Yeah, just -1 times this plus 0 times each of those. So just negative x squared. But then x is 0, right? So that's going to be 0 also. That means that that integral is also going to be 0. Okay, so we have 72 plus 0 plus 0. And we just have this front part, right? This front part. Okay, so the front side. What's the equation for that? What's the equation for the front side?
Y equals 0.
Yeah, x equals 2, right? Because that's where x is 2. X equals 2. Okay, whereas the back one is x equals 0, this is x equals 2. Okay, what's a normal pointing out? So it's pointing, so it'd be pointing this direction. Normals would be pointing this direction, right? Parallel with the x-axis.
Will it be like 2, 0, 0?
Yes, 1, 0, 0. Okay. You're on the unit normal, is what you're after. Okay, so now f dot n. So I take the dot product of f with this. I'm going to get, what's that going to give you? So this one, dot product with this. It'll be this, or it'll be x squared times 1, right? So x squared plus who cares times 0 and 0. So just x squared. But we know x, but this is going to be what? We know x is 2, so this will be 4, right? So the integral okay, now we're integrating over this pink surface area, but actually over the orange one is what we're integrating, because we can project it down into the YZ plane, right? We can project it down into there. So, and then we can put it into polar coordinates. So r is going to go from 0 to 3, and theta is going to go from 0 to pi. Okay, so like here's 0, here's pi over 2, and here's pi. So we're just going over that, and then we're going from 0 to 3. Okay, so 0 to 3, and it's just 4 r dr d theta. Okay, and then since we know that there's no thetas in there, then, and we just go from 0 to pi, then it's just going to be pi. And then the other part is what? 2r squared from 0 to 3. So that's pi times, what's that, 9, 18? 18 pi, whoa. Okay, so try as a final answer. So there's this 72, that 0, and that 0, and that 18 pi. So 72 plus 18 pi.